Okay, now, you gonna give any more homework for this class, or this was the last homework?
This is the last homework.
Homework was the last.
Yeah. Yeah, from here it's just working on the final project.
And you don't consider marks for the lowest homework, right?
Um,
When you calculate, or you?
I removed the lowest homework, so that one's removed from your grade.
Okay, thank you.
Mhm.
No, very happy. Big rice, or Irabi, or Irabi, sounds like bacon. Yes. I heard Irabi's good. Actually, do come across some more points in your building. So, well, I do actually like do like calculations and stuff. If it's a class, and I feel like it's gonna focus on that. Well, what do you do? Docs and methods, so I design those. For some of the business. Building, also workers. So, yeah. Okay. You guys are hiring later on. Yeah. So I feel like once I finish this, then they'll call me. Yeah. But that isn't. They're hard to get into for engineering.
All right, it's 7:30. Let's go and get started. I mean, 5:30, sorry. I wish it was 7:30, then I can go home, but all right, so good evening, everyone. How's everyone doing?
Good.
Good. All right, so today's a busy day. So we have a lot to discuss today. So hopefully everyone got my emails today. So we have a midterm exam. Our second midterm is gonna be next Thursday, April 25th, okay? The content for the exam is gonna be basically all the stuff we've been covering recently. Everything that was covered on the last homework assignment, so that's strong forms, weak forms, finite element forms, and Gauss quadrature, okay? Format for the exam is going to be same as the last exam, so there's going to be a problem solving portion as well as conceptual question portion, and everything you can bring is the same as the first exam as well. So writing utensil, calculator, cheat sheet, both sides, all good stuff. Okay, so I posted a study guide onto Canvas, and so definitely make use of that as you begin your studying. But if you study the most recent homework assignment as well as the study guide, you should be good to go for the exam. Okay. All right. So what I wanted to do today, I wanted to spend the first part of today talking about the final project, and so that was kind of the other thing that I posted today. The final project's not going to be due until May 20th, and so we still have a bit of time. But it's good to kind of think about what the project is all about and kind of what you're going to be expected to do. Because a lot of what we're going to be doing over the next few weeks is just kind of preparing for the project and covering the information that you need to do for the project. Okay. So it's good to kind of know what you're going to be applying it to, so that you can kind of see, as we're kind of going over in the class, you can kind of see it, how it's being applied on the project at the same time. Okay. And then after that, I think we'll probably have maybe about 30-45 minutes left, and then we're going to cover our next topic, which is introduction to 2D finite elements. All right, any questions on any of this? Yep.
Is there any MATLAB stuff on the exam?
No, it's all hand calculation.
Okay.
Yeah.
Is the coverage for that kind of from last week, or are we also, I guess, stuff from this week on the exam too?
Nothing on from this week on the exam. So the cutoff for the exam was everything from last week. Yeah. Yeah, so it's all 1D stuff. Yeah. 1D stuff and Gauss quadrature.
Oh, can we get solutions posted?
Yes. Yeah, so I'm working on those. I'm just working on formatting it a little better. Then it'll be posted probably tomorrow.
Oh.
Okay. All right. Any other questions on the upcoming stuff? Okay. All right. Let's talk about the project. Let me go ahead and switch to my computer screen here. Okay. So I posted this document onto Canvas today, and so if you go to under assignments, you should see that the final project assignment is activated now. Okay, and then on there's a lot of files here, and so there's a lot of starter code. There's a grading rubric and a template, but the main document that you're going to be following for the instructions is this one right here. Okay. Oh, I thought I changed that. So obviously it's not fall 22, it's spring 2024. The due date is updated, so it is due on May 20th, 2024. And this is the project that you're going to do. Okay, so obviously, it's a spin-off of the project that was offered that I gave about 2 years ago. It's just different geometry and slightly different stuff. Okay. So the whole idea for the final project for 541 is to write a MATLAB code to solve a 2D finite element heat transfer equation. Okay, so I'm going to be giving you this mesh, right? So this mesh is going to be a 2-dimensional mesh. It's basically just a plate with a slot in it. Okay, so it's a rectangular plate with a rectangular slot. You can see here that it's meshed, right? And so very, very similar to how a geometry would be meshed in ANSYS. And you're going to be running a simulation. The only difference here is that you're going to be writing the code to run the simulation, right? So over the next couple of weeks, we've so far we've kind of already built the foundation in terms of how to solve 1D general finite element problems. And so over the next 2-3 weeks, we're going to be going over how to do this in 2D as well. Okay. So right now, at this moment, you don't have everything that you need to do the final project. But I did want to assign it now and give you the information so that you can kind of know what to look out for over the next few weeks. Okay. Because we don't have a final exam in this class. It's just the final project. And so this is going to be the major thing that's going to factor into your final grade. Okay. Just to give you a little bit more motivation to kind of for the next few weeks. Okay. And so since these elements, these elements are going to be generated with the generic kind of geometry mesher. So we're going to use a meshing tool within MATLAB itself, right? And so that means our elements here are going to have an arbitrary shape and an arbitrary orientation. So we're not really going to have much control over it. Okay. Actually, we are going to be able to know ahead of time that our elements are triangles. So we know the shape, but we don't know exactly kind of the orientation and the size of the elements. Okay. And so over the next couple of weeks, we're going to be learning a method called the isoparametric approach, okay, that we can use to solve this that we can use to solve this problem, right? So the isoparametric approach is pretty much ubiquitous. Basically, all finite element softwares use it. I can guarantee you it's used in ANSYS to some degree, and so it is a very kind of powerful method, a very kind of powerful approach to do problems like this, where you have an arbitrary geometry with an arbitrary mesh. That you need to solve the simulation. Okay. So a lot of this information on the document here is information that we're going to be covering over the next few weeks. And so I don't want to dwell too much onto it, but this is basically how the isoparametric method works. So you basically take your element physical space, you map it onto what I call kind of a parametric space, which is kind of a very standard triangle. And then you build your element stiffness matrix based on this, and then you map it back to the physical space. Okay, so it's kind of a big thing. Okay, so we are going to use a specialized tool in MATLAB to help us out with the geometry and the meshing. And so likely if you're running a version of MATLAB at home, you probably won't have this installed. If you're going to be using the computers here on campus, we do have this installed already. And so that tool is called a PDE toolbox. Okay. So you can install it, and so if you have MATLAB installed through the school license and through what you got from school, you should be able to install this. And so on MATLAB, if you open up, there is an apps button here. Okay, and what you can do is you can get more apps, and then if you just search for the partial differential equation toolbox, then you should be able to install it from there. Okay. So what installing this toolbox does is that it loads in a bunch of kind of pre-packaged functions that we're going to use for generating the geometry and making the mesh. Okay. All right, and so this is the equation that we're looking to solve here. So we have a two-dimensional heat equation with a thermal conductivity K and a thermal generation X, S of X, okay? And this is the thermal generation function that we're going to be using, okay? Okay. So how are we going to write this code? So it is a fairly big code, right? So this is going to be the biggest code that you're going to write in class. And so to kind of make it to kind of stage it for you guys, so you're just not writing one massive code, I've broken it down into 3 parts, right? So there's part 1, part 2, part 3. And in each part, we're going to add kind of more complexity and more features to it. Okay. So in part 1, at the end of part 1, we're going to have a fully functioning code. But we're going to be doing it for the simplest case that we can think of. So that is a case with simple diffusion and Dirichlet boundary conditions. Okay, and so we're not going to have any Neumann boundary condition, no heat flux boundary condition, no thermal generation. So we're just going to solve kind of a very basic case. Okay. Okay, and so to that end, let's look at the starter codes, and so you can see I posted these for you here. It'll load. Oh, that's awkward. Okay, let me download it and we'll open it now. Okay, so the starter code is kind of intended just to get you started. Okay, so I've kind of done a lot of the formatting and a lot of the structure of the code already for you. And then you just have to kind of fill it in. Okay, So the way to read the starter code is that I have a lot of sections of the code that have this comment called to do. Okay. And so whenever you see to do, that indicates basically that you need to put some code in. Okay. All right. So here it is. Okay. So the exact format of the code is actually, you know, I designed it to be kind of somewhat similar to the codes that we've gone over in class together already. So just like the frame code, the truss code, and the 1D code that we did last week. Okay. So at the very top of the code here, we have all of the problem parameters. Okay. We have a section for defining the boundary conditions, right? There's a lot of added code here for the mesh, and so processing the mesh and getting the information for the mesh is going to be, quite different. I think that's probably the biggest difference, right? But you can see here that we have data structures here for the global stiffness matrix, for the global forcing vector, for the element forcing stiffness matrix and the element forcing vectors. Okay, and this is where you're going to write most of your code here. Okay. Okay, so we have a loop for generating all the element stiffness matrices and all the element forcing vectors. Okay. We have a loop for the assembly. We have a loop for applying the boundary conditions for the solution. And then down here, I've plotted the solution for you here. Okay. So because we're using the PDE toolbox, you know, the PDE toolbox actually has a way to solve these equations already. Okay. And so we're basically going to be regenerating or basically recreating those results using the theory that we found in the class. Okay. So when you run your code, basically two figures are going to show up, or two main figures. You're going to have one figure that shows your solution, and you're going to have a figure that shows what's called the reference solution. Okay. And if you did everything correctly, if you coded everything up well, then the two figures should match up. Okay. So your reference solution should match up with the with your solution. Okay, so here are the boundary conditions for the reference part. And so you're going to on edges 1 and 2, which are these two edges right here. So it's a little bit hard to see, but if you zoom in on this figure, you'll see each of the edges are labeled with different numbers. So edge 1 is this one right here. Edge 2 is this one. That is going to have a boundary condition of 100 degrees Celsius. And then edge 6 and 7, edge 6 being this one, edge 7 being that one, is going to have a boundary condition of 100 degrees, 25 degrees C. Okay. Okay, so that's part 1 of the code there. And so here's just a little bit more information about the data structure that you have. These are, you know, all of these we've seen before, you know, in previous codes, just that, you know, now they're kind of ramped up a little bit just because the number of elements and nodes is quite a bit. Okay. So of course you see a return of the connectivity matrix, right? So remember this was a thing back in our truss codes and our frame codes. Okay. We have K global, F global, K LM, FLM, right? So all data structures, you know, for the most part that we've seen before, it's just that, you know, they're a lot bigger now because of the nature of the mesh. Okay. Another thing that you'll notice in the starter code is that there are data structure for Gauss quadrature. Okay. Okay, so that's the GP vector here, and so you're going to need to incorporate 2D Gauss quadrature into the code as well. All right, any questions on this so far? Okay. All right, so that's part 1. So part 1 is the basically kind of the nuts and bolts. And honestly, probably you'll spend you know, most of your time in part 1, and part 1 is worth the most points too, between parts 2 and 3. Okay. Because in part 1, you have to make the element stiffness matrices, the element or excuse me, just the element stiffness matrices, you have to do the assembly and the boundary conditions as well. And that means Gauss quadrature as well, right? So part 1 is the biggest portion, but it is worth the most points. Okay. In part 2, you're going to modify your part 1 code to incorporate thermal generation as well, right? So we have a thermal generation function here, 1000x minus 5000y, okay? And so again, you're going to utilize isoparametric elements in Gauss quadrature to integrate this term together with the shape functions in the element to add this to the element forcing vector. Okay. So part two, I think is probably the least amount of work compared to part 1. It is a lot smaller. And then part 3, the final part, which is actually the hardest part, is to incorporate Neumann boundary conditions. Okay. So the thing with Neumann boundary conditions in 1D, these are fairly simple. We just kind of add their values to the matrix. But what you're going to see in 2D is that because in 2D, we have, our elements here, when they're bordering an edge, right? When they're bordering a boundary, they actually border on a whole edge instead of just a point, okay? And that actually changes the nature of how we apply this Norman boundary condition as well. So we're going to talk about that over the next few weeks about what that means. I think conceptually, it's not too difficult of a concept to understand. We'll talk about it a lot in the class. It's just that programming it and making sure that you're applying it on the right edge, and first of all, even just applying it on the right elements to begin with, is going to be a challenge, right? And so that's why part 3, the tutorial for part 3 is the longest. And so there's kind of a lot to go on here, and you have to apply kind of a special Gauss quadrature rule on this as well. Okay. So part 3, I think part 3 is the most difficult part of the code, just because it involves kind of the most programming, and it's kind of, we haven't really done anything like it. So you want to make sure that you save yourself enough time. You kind of try to get through parts 1 and parts 2 kind of as quickly as you can, so that you have enough time to do part 3 at the end. Okay. All right. Any questions on this? Okay. All right, so there is a bonus part. So I don't offer extra credit very often. This is probably one of the only times I've offered extra credit in the course, but I am offering extra credit on the project as well, right? And so to get extra credit on the project, you have to improve the efficiency of the code itself. Okay, so I want to make clear this part is not required at all, and so it's very possible to get 100% on the project, and get an A in the course without doing this part. And honestly, this part is just only for just an additional 10 points, 10 points on top of 150. So it's actually a very small one. So it's honestly just kind of a badge of honor to do this part. But the way I've kind of structured this code right now is actually very poorly optimized. So it doesn't make good use of memory, and it definitely doesn't make good use of time at all. And so, by the end of part 3, you're going to have 3 separate loops that go over all the elements. You're gonna have a loop for the element stiffness matrix, a loop for the thermal generation, and the assembly loop. Okay. So there's really no reason why we should have 3 loops like that. And so in fact, you can actually combine all 3 of those parts into one loop. The only reason I kind of separate into 3 parts is just to kind of stagger it for you guys. Okay. So if you can combine all 3 parts into one loop and improve the memory usage, then I'll give you 10 points extra credit. Okay. And so what I mean by memory storage is that there's really no need to store every single element stiffness matrix and element forcing vector, right? And so you can kind of compute those temporarily within the loop and then assemble it right away. Okay, because if you do that, right, then you're going to be able to save yourself on a lot of storage, right? Because if you look at the codes that we've written before, this applies to the frame and the truss code as well, right? All of those codes had a data structure like this, right? Which is basically a 3-dimensional matrix. And so, and the purpose of this was to store every single element stiffness matrix that we generate, right? So for for all the frame and the truss codes and the 1D codes, this was not that big a deal because we didn't have that many elements. But for this project, we're going to be generating, probably close to, a few hundred different elements, right? And so storing, a few hundred different element stiffness matrices is a huge waste of space. And so if you can modify the code to kind of, eliminate those 2 inefficiencies and make it better, I'll give you some extra credit for that. Okay. So of course, the reason I'm making this extra credit is that, this class, even though we're doing a lot of programming, this is not really a computer science class. And so, we don't really talk about optimizing code. But it has bugged people in the past. And so, people have asked me, why is this code so poorly written? And I'm like, yeah, it's not supposed to be a performance code. It's an educational code. So if it bothers you, you can fix it, you can make it better, and I'll give you 10 points for it. Okay. Okay. So to summarize, these are all the different, kind of main programming parts that you have to do, right? So you have to set up all the data structures. You have to compute the element stiffness matrices, which is part 1. Compute the element forcing vectors, part 2. Okay. Compute the element forcing vectors associated with Neumann bound. This should be part 3. So I'll need to kind of revise this a little bit. Okay. Assemble the global linear system, apply the boundary conditions, and solve. Okay. All right, any questions on, any of the three parts there, part 1, part 2, part 3, or the extra credit? Okay. All right, so let's talk deliverables. Okay. So this is going to outline all of the basically all the plots that I expect you to have for the report. Okay, and it's also separated here in terms of the parts. And so that's why I kind of give you 3 different starter groups, right? Because on the one hand, I want you to compare your results at the end of part 1. Okay, so I want you to compare your own computed solution with the reference solution. Okay, and so I want you to comment if these 2 plots match, if there's any discrepancies between the solution. Okay. There should be, one small difference between the solutions. I'm not going to tell you what it is right now, but there should be one difference, right? It should hopefully become clear kind of as you're doing the project, and and so hopefully you notice it, and hopefully you can kind of explain why this is. Then you're going to compare the results at the end of part 2, and so once again you're going to compare visually what the 2 fields look like. There's going to be a way to compare it numerically as well. Okay. And then finally, you're going to compare the results at the end of part 3. So you finish part 3, you're going to show both temperature fields and compare the results. Okay. Okay, so there's a few more plots that I want you to show. And so another plot that I want you to show is a comparison between mesh densities. And so because we're using a built-in meshing program within MATLAB, there is a way for it to control the mesh. And so I want you to perform a mesh convergence test, where you basically run the simulation with the different amount of mesh elements and you basically compare the results. Okay. In part 5 right here, I want you to change one of the boundary conditions. And so, for all of the parts 1, 2, 3, I basically set the boundary conditions for you. But I want you to see kind of what it would look like if you change the boundary conditions. Okay. So that's what you would do there. Okay. And then if you do the bonus part, if you do the extra credit, you can compare, right? So there's a way for you to time your codes, and so I want you to time your code. And so if you make all of the requisite improvements, you should see a pretty significant improvement in the performance, and so it should run a lot faster compared to the format that I have. Okay. So you should be able to kind of show both differences and kind of explain kind of the changes that you make. All right. Final report. And so the main deliverable that you're going to hand in is a final report. I also want your codes as well. So please submit your codes for part 1, part 2, part 3. Okay. So there's no page limitation on the report. So I don't count the number of pages. That doesn't really factor into the way I grade things. I'm mostly looking at the content and making sure everything is there and explained in sufficient detail. Okay. If you want a rough average, and so most reports kind of end up in this range of being about 12 to 15 pages. And so that includes figures as well. Okay. And I'm going to provide a template for the final report as well. Okay. So audience, right? So whenever you write a report, it's important to know who your audience is so that you can write it effectively. Okay. So you can assume that your audience has a relatively strong basis in math and science. And so usually what I tell people is that, imagine your audience or imagine you're writing this report to kind of explain what you're doing to yourself, but prior to you taking the class, right? So think about kind of, how you were back in January, and you're writing yourself a report to kind of explain, what this project is about, what this class is about. Okay. So your audience knows everything that you knew back in January. Okay. So the sections of the report, these are pretty standard stuff. We have an introduction, we have a methodology, we have a results section and a conclusion. Okay. So pretty standard fare. Part of your grade is going to be on general aesthetics, and so that is good formatting, good spelling, good grammar and everything like that, right? Don't use ChatGPT. It's very obvious when I read a ChatGPT report, so please don't do that. Okay. So make sure you're writing it yourself. All right, teams. So there are no teams. So this is an individual project. So everyone is going to write their own code. Everyone's going to write their own report. Okay. With that said, everyone in this project's unique because everyone's working on the same code. So you can't don't copy off someone's code, but I'm fine with you guys working together with the classmates. And so if someone's having an issue, something that you could help them with, you can feel free to help them, but don't let them copy your code and don't ask to copy someone's code. Okay. All right. So final remarks. And so, this project is a lot, it's a lot of coding. I built in kind of some time at the end of class, at the end of the semester, probably the last 1 or 2 lectures that we have to work on the project. So my biggest advice is to just not procrastinate, definitely start early. You're going to run into issues with the project, with the coding, with the formatting, with anything. So, it's always good to start early, kind of, run into your issues, get help from me, and just so that you can continue. Okay. So, I know, for this project, I am asking a lot. It is a lot of coding to do. But with that said, I am going to be there with you guys kind of every step of the way. So, definitely don't be afraid to ask for help. It's just that generally it's a lot easier for me to help you if you start early, right? So as you can imagine, if you kind of wait until the last minute, a lot of people do that. And so the last week before the project is due, I just get bombarded with just a ton of emails, and everyone wants me to look at their code and to fix an error, things like that. So, you'll get a much faster response from me, a much less irritable response from me if you ask me early on. Because those last few days before the project is due is everyone's stressed, and so I get it. People email me, they're upset, they're frustrated, but so I'm upset. I'm usually kind of upset and frustrated. I try not to be, but so if you ask me earlier on, then I'm much more likely to give it more of my time. I'll say that. Okay, so again, the due date for the project is Monday, May 20th, and so that is the Monday after finals week. So that just because I know that everyone's always busy during a finals week. I know you guys have exams and other projects to work on as well. So I'd like to give you guys a couple extra days, at least at the very least that weekend and then Monday to kind of for you to kind of finish up writing your report. Okay. But what that means basically is that I can't really push this back at all. And so basically right after you guys turn it in, I have to grade basically everything. And so that includes you guys and the 2 other classes that I have. So I can't really push this date back because I do have to finish grading by the Friday of that week. Okay. So this is, I've basically pushed this back as far as I could. Okay. All right. Any final questions on the project? Okay. All right. So definitely get started with that. At least at the very least, take a look now. Of course, we still have a lot to learn in order to about 2D finite elements for you to really kind of get started in earnest. But at least looking at the code and kind of getting familiar with the data structures and the format, I think will help. Okay. And if you're curious as well, I do have the rubric here. Oh wow, I changed it to one, but not full. Okay. Anyway. Okay, so you can see here, this is how the grades are broken down. Okay. So a lot of the report is going to be based on how you write it. Okay. So basically how you explain the methodology, how you explain the introduction. Okay. You can see for the results, the majority of the points are on part 1, then part 2 and part 3 are worth slightly less. Okay. And there's a big portion for the aesthetics as well. Okay, so making sure your report is clean and well organized, grammatically sound, no chat GPT, all that good stuff. Okay. All right. So that's the final project. Let me go ahead and bring it back to.
So it's like the actual code file have any weight?
It does. That's part of the results.
Oh.
Yeah. Yeah. So make sure that you are writing your your code. You're not just getting the figures from someone else. So I do run all of your codes to make sure that what you get matches what we have. Of course, my OneNote decided to update right now. Great time. Okay. All right. So as you can see, from the final project that, it's all about 2D finite elements. And that's basically what we're going to be doing for the rest of the semester. So let's get started with that today. Okay. So what I wanted to cover today is some of the mathematical preliminaries to, to doing multi-dimensional FEA. Okay. All right. So last week, last time we met, we just about finished up doing 1D finite elements, right? And so we learned how to take a differential equation in one dimension, discretize it using a finite element mesh, generate your element stiffness matrices, element forcing vectors, assemble, and all that good stuff. Okay. So basically from here, we're going to take that same process, the same process that we did in 1D, and apply it to 2D problems as well. Okay. So we're going to be taking two-dimensional partial differential equations and discretizing it according to the finite element method. Because all the differential equations that we've seen up to this point, everything we did with the strong form, weak form, finite element form, those were ordinary differential equations because there was only one independent variable. Okay. When you move to 2D and 3D, and even when you get to unsteady problems, the number of independent variables is going to increase. Okay? All right. So if we look at it at an example in 1D, so in 1D, we had a situation like this. We had k times a d squared t dx squared plus s of x is equal to 0. Okay. Okay. So you can see here this is an ordinary differential equation, right? The way you know is that our derivatives here are just kind of standard t's, right? But most importantly, if you look at the independent variable for the derivatives, there's only one, right? Which is x. Okay. If you compare that to a PDE, right? The standard PDE is something like this. And so you're going to have partial derivatives instead. Okay. And so one thing you'll notice that all the derivatives here are partial. But the number of independent variables is going up by 1 as well. Okay. And so instead of just taking derivatives with respect to x, we're also taking derivatives with respect to y as well. Okay. And so that's what makes this a PDE, a partial differential equation. Okay. Some other common independent variables are z if you go up to 3 dimensions, and time if you do an unsteady problem as well. Okay. Oh, thank you. So s is a multi-dimensional too. So s needs to be a function of x and y. Thanks for catching that. Yeah. Mm-hmm. Okay. And so since we're making this jump from 1D to 2D, all the concepts are still the same. It's just that, doing derivatives in higher dimensions and doing these partials, it requires a little bit of a review, I would say. Okay. And so all of a sudden, we're not just doing regular calculus now, we're onto multivariable calculus. Okay. And so with that comes, some additional operators, some additional theorems that we have to kind of take into account. So what I wanted to accomplish in this class was just to kind of review, just do a very kind of quick review of some very key concepts in multivariable calculus to kind of prepare us for doing 2D FEA. Okay. Okay. Any questions on this so far? Okay. All right, so first let's go over just some basic definitions. The main thing that I want to cover is kind of this notion of the boundary. The boundary is really important because that's how we're going to be applying our boundary conditions. Okay. So let's look at what we let's look and see what we define as the boundary for a 1D problem, right? So in 1D, okay, that's our typical 1D domain, right? So we have just a line, and our boundary are just the two nodes at the ends of the line. So this is our boundary, and this is our boundary. Okay. So this made our lives pretty simple when we're doing problems, right? And so that means our boundary condition can only be applied in one or two places, right? And in fact, our boundary conditions are only applied at a single node, right? Because our boundaries are only single nodes. Okay. Now let's talk about 2D domain. So a two-dimensional domain is a two-dimensional shape, right? So it doesn't have to have any specific shape, so it can just be an amorphous blob. Okay. I had a professor in college that always referred to this as the arbitrary potato, and it always makes me laugh. I was like always giggling in the class. He always got mad at me. He thought I was making fun of him. It's just funny. It's an arbitrary. It's called an arbitrary potato. He's talking about just advanced mathematics and stuff like that. All right. Anyway, okay. So we have a two-dimensional domain like this. Okay. Now, if you ask someone, right? So you ask any person on the street, if you look at this domain right here, you look at the shape, and you ask them what the boundary of this shape is, right? They're not gonna identify single points. What we have instead is a line, right? So the boundary of this domain consists of the line that kind of surrounds the entire domain. Right? Okay. Now, this is going to be a lot more complicated for us, right? Because instead of just applying our boundary conditions at specific nodes, right? Imagine what this is going to look like after we mesh it, right? So think back to just 20 minutes ago when we were looking at the final project, right? Whenever you have a line, right? Depending on the mesh, you would have lots of different points on the line. Right? I don't know why I went through and put all those points there, but now it looks nice. Now you can actually see all the different points, right? In fact, depending on how you mesh it, you may have even more points on the line, right? So it all depends on how your meshing is. So unlike in the 1D case, right? In the 1D case, we knew exactly how many boundary points we have, right? It doesn't matter how finely you mesh your line, right? The line is going to have a starting point and an ending, no matter what, right? There's going to be two boundary points. In 2D, we don't know how many points are going to be on our boundary ahead of time. And that's really significant because, in FEA, the points or the nodes of the mesh are very important in our solution, right? And so, if you think back to our global element stiffness matrix, right? Each line or each row in that matrix corresponds to a different node, right? And so when we were applying the boundary conditions on that, we knew exactly we need to modify the first row and the last row, right? In 2D, that becomes a lot more complicated because we don't know, first of all, we don't know how many rows we're going to modify. And a lot of times we don't know exactly which rows we're going to modify as well, okay? So now the issue of applying boundary conditions becomes a lot more complex just because our definition of the boundary has become a lot more complex as well, okay? So of course, we're going to be, talk about methods for doing this, okay? It's just that, I want to kind of illustrate that problem to you, okay? One other really important concept that that's really important for the boundary is this aspect of what's called the outward unit normal, okay? All right. So anywhere on the boundary, we can draw a vector that's perpendicular to the boundary that points outward, okay? So this n hat right here is called the outward unit normal. And so like the name implies, it's a vector, right? It's a unit vector. So it has length 1, right? And the purpose of that unit normal is to point outside of the domain, right? So the exact direction of the unit normal depends on the element, right? And so the outward unit normal for this element is going to point this way. The outward unit normal for this element is going to point this way, okay? So we can say that the direction of the outward unit normal changes for each element. And it's always perfectly perpendicular to the surface element. So this concept, this concept of an outward unit normal, probably you guys have seen this in some of your other courses as well. This concept of an outward unit normal is going to be really important to our formulation, especially for the Neumann boundary condition. Right? So this is definitely something that's going to come up again. Okay, and so how it's going to come up is that when we derive our equations, you're going to see some things like maybe delta t dotted with n hat. Right. And so whenever you see n hat appear in an equation, that's what it's referring to. It's referring to an outward unit normal. Okay. I just want to prep you for that as well. The reason for that, the reason we have that outward unit normal is that, when you talk about 2D, this notion is there for 1D as well. It's just kind of implied. Is that when you talk about 2D and 3D finite elements, this notion of having quantities enter and leave your domain is actually very important, especially when you're applying the boundary condition. So having some direction in terms of the outward unit normal is very important. Okay. All right. Any questions on this so far? Okay, good. So we're not going to cover in detail, but of course, all of these topics, extend to 3 dimensions as well. So in 3 dimensions, as you can imagine, it's even more complicated. And so the boundary of a 3-dimensional domain is a surface instead, okay? Which is more complicated than normal. And so when you get to 3D, it becomes a lot more challenging. Okay. All right, so let's review some important vector calculus operations and what they mean. Oops. Because another thing that you're gonna have to get used to once we're working in 2D and 3D is the notion of vectors, right? So of course, we just mentioned it with the use of the unit vectors, but a lot of things in 2D and 3D are described as vectors as well. Okay. So the simple example of this is deformation, right? And in fact, we've already kind of seen this in our direct stiffness unit. So if you have a one-dimensional spring, right? The only way it can deform is left and right, right? And so when we compute the deformation dx, okay, that was the only way that it can go. In 2D, right? So let's say that we have a truss structure like this. Okay. And so let's say that we computed the deformations of the two nodes up here. We knew, just because the structure is two dimensions, that there's a dx component and a dy component, right? So this would be dx1, dy1, dx2, dy2. Okay. And so our deformation is no longer a scalar quantity, it is a vector quantity, right? So it has x and y components. Okay? And so that same notion applies to a lot of things, okay? There is one key quantity where this doesn't apply to as well, or it doesn't apply to, and that is the notion of temperature. Because unlike deformation, temperature is known as a scalar quantity. Okay? And what that means is that it doesn't have any direction, it's just the temperature. Okay. So this is nice. And so what a scalar quantity basically means that even if you are solving equations in 2D and 3D, temperature is always going to have this one component. And so that makes our governing equations actually a lot simpler. Okay. So if you may have noticed kind of the subtle shift. And so over the last few weeks, we've kind of subtly been shifting from structural equations to thermal equations. And then as we go further into 2D, we're gonna make that transformation complete. Okay. So it is very possible, of course, to solve elasticity and deformation equations in 2D. It's just because deformation is a vector quantity, it just becomes a lot more complicated. Okay. And so, from basically from this point out, we're going to be strictly solving the heat equation. Okay. Just because the heat equation is just, honestly, it's just the easiest PDE to solve in multiple dimensions. Just because, because deformation is a vector quantity, there's actually multiple PDEs that we'd have to solve simultaneously, which you can do. It's definitely possible. It's not impossible. It's just It's just a little bit too much detail, a little bit too much complexity, just kind of for what we're trying to accomplish, right? So from here on out, you're no longer going to see any structural equations. It's just going to be the heat equation. Okay. Okay. But even with a scalar quantity like temperature, we are still going to apply some operators of vector calculus to it. Okay. And so I wanted to take a moment to review, what are some of the important vector operators that we need to know. Okay. The first one is the gradient. Okay. So the gradient is like, you can think of it as like an expanded derivative operator. Okay. The reason we have this is because, when you have a quantity and you're modeling it in multiple dimensions, you can compute the rate of change in each of those directions. Okay. And so let's say that we have kind of a rectangular domain like this. Right. And we have the temperature. Okay. We can compute how that temperature is changing in the x direction with the derivative in the x direction. Okay. So partial t partial x tells us how our temperature is changing in the x direction from that particular point. Okay. And then partial t partial y will give us the rate of change of our temperature in the y direction from that specific point. Okay. Right. Because in multiple dimensions, we have this notion of partial derivatives in each direction. Okay? So the idea of the gradient is to kind of, kind of combine all of these into one kind of thing. Okay. The important thing to remember about the gradient is that a gradient operator always increases the dimensionality by one. Okay. Increases the dimensionality of your quantity. All right, and so let's say that we have T, right? Temperature. Temperature is a scalar quantity, so it has only one component, right? So even a temperature that's a function of x and y, at a specific location x or y, x and y, excuse me, and then we're only going to have one value of temperature. Okay. So this is a scalar. Okay. If we were to take the gradient of this, and so the symbol for the gradient is this upside down triangle, which we call a nabla. Okay. So if we were to take the gradient of the temperatures, we take nabla t, this changes our scalar into actually a vector quantity, right? And so this vector now, we have two components, where each component is the rate of change of the temperature in each specific direction, okay? So this is now a vector. Okay. But you can kind of see why I call it kind of an expanded derivative, because, oftentimes, when you're in a multi-dimensional case, and you take the gradient, that basically tells you the rate of change in every principal direction, okay? X direction, Y direction. And that's kind of how we do it. Okay. All right. So you take the gradient of a scalar, you get a vector. I'm not going to write it out, but you can imagine if you take the gradient of a vector, you're going to get a matrix from that. Yeah, question.
What was the name of that triangle again?
Nabla. I'll start there. Yeah. So if you're using kind of Microsoft equation editor and you want the shortcut for making that upside down triangle, you do \nabla. Okay. So gradients always increase the dimensionality by 1. Okay. All right, any questions on gradients? All right, good. All right, the next one that we're going to cover is divergence. Okay. So the divergence, it's an operator involving the nabla again, but instead of taking our scalar point and turning it into a vector, basically the divergent does the opposite. Okay. So the divergence basically utilizes the nabla operator together with the dot product to actually reduce the dimensionality of a vector by 1. Technically speaking, you can use divergence to reduce a matrix into a vector, but that's, we're not gonna do that. So we're mostly gonna be using this to reduce the a vector into a scalar. Okay. And basically, the way it works, or what it looks like, is that you're going to add together all of the partial derivatives of each component of your quantity. All right. So let's say we have a vector u, or let me call it d, just so it's consistent. Okay. And so this vector has, we'll say, has 3 components, and so we'll be in 3D. So we have dx, dy, and dz. Okay. So the d vector looks something like this, right? It has its x component dx, its y component dy, and a z component. It's impossible to draw, but imagine there's a z component there as well. Okay. So if we take the divergence of this, right? So the way to notify the divergence is to take nabla dot product with a vector. Right? Okay. So the way that we do this is we take the partial derivatives of each component with the independent variable associated with that coordinate. Okay, that's a very fancy way of kind of showing kind of a very simple fact, right? So let's take the x component first, right? So we're going to take the partial derivative of dx with respect to x. Okay, so partial dx partial x plus partial dy partial y plus partial dz partial z. So that right there is the divergence operator. All right, so physically, kind of what the divergence represents. Honestly, probably the easiest analogy I can probably come up with for you guys is from fluid mechanics, and so it's used in conservation of mass a lot. So the divergence is used to kind of specify whether a fluid is kind of expanding its domain. Okay, and so one of the most common forms for the divergence is in fluid mechanics. And so if you have an incompressible fluid, that's, in other words, a fluid that's incapable of kind of expanding its volume for a fixed amount of mass, right? Then you say its divergence is equal to 0. Okay. For us, in finite elements, we're mostly going to use divergence as kind of a mathematical tool. But it does have some physical significance in certain fields. All right. Actually, the main way we're going to use the divergence is to create something called the Laplacian, which is the next thing. All right. Any questions on the divergence? Okay. All right. So the last quantity or the last operator that I wanted to review is one called the Laplacian. So the Laplacian is kind of the combination of the two previous operators, right? So we know that if we take the gradient of something, we take a scalar quantity, we turn it to a vector. And then if we take the divergence of a vector, we turn it back to a scalar. So the Laplacian kind of combines both, right? So if we take the divergence of the gradient of a quantity, okay. So we go from a scalar to a vector by taking the gradient, and then by taking the divergence, we go from a vector back to a scalar. So it kind of seems like we're back to where we started with, right? Okay. So we end up with a scalar quantity, but that's just not any scalar quantity. So what we're going to end up with is basically a summation of all the second order partial derivatives of that particular quantity. Okay. All right, so let's map this out. So let's start with the scalar quantity t, just like we did before. Okay. So if we take the gradient of t, that's going to give us a vector quantity, right? Then on that, let's take the divergence just like that. Okay. So we have the divergence of a gradient. Right. So this particular operator occurs a lot in applied math. In fact, it's kind of the exact form of the heat equation, and so we have a special symbol for it. Okay. The symbol doesn't, it doesn't really make any sense considering what Nabla is. It's just kind of a convenient shorthand. It looks nice too. So anytime you see like a complicated mathematical equation in like a Hollywood movie, you see the Laplacian, just because it looks mathematical, I guess. Okay. And so what it looks like is the following, right? Oh, should be Nabla squared t, excuse me. Okay. And my notes I have, but I'm trying to stay consistent with t. Okay. All right, so it looks like this. And so it looks like the divergence, right? So it looks like this, except instead of first derivatives, we have second derivatives, right? So we kind of have two layers of derivatives, one from the gradient, one from the divergence. Okay? So this is partial squared t, partial x squared, plus partial squared t, partial y squared. Okay. If we were in 2 dimensions, that would be it. But I'll go ahead and show you the 3-dimensional version as well. So that's partial squared t, partial z squared. Okay. But of course, if you're just talking a 2D problem, then that last component isn't there. Okay. So this form right here, this form of a combination of partial derivatives, this shows up very commonly in a lot of our governing PDEs that we like to solve as engineers. So it shows up in the heat equation, it shows up in the Navier-Stokes equations, it shows up in the structural equations as well, albeit then in that case, it's applied to a vector quantity. But this Laplacian is a very common thing. Mostly just because, physically it models the process of diffusion, which is a very common physical phenomenon. Okay. So that's just kind of a very brief review of these kind of operators. And so the reason I'm doing this is because, as we kind of develop the equations for multi-dimensional heat transfer, you're going to see me use these symbols a lot. And so I want you to kind of know what they mathematically represent, as well as kind of a little bit of physical intuition behind them as well. Okay. All right, any questions on this? Okay, so the last thing that I want to talk about today for the last 10 minutes is Green's theorem and Green's formula. Okay? So you may have learned this back in multivariable calc a long time ago. Probably it's in the deep recesses of your brain because you probably never used it up to this point. But we are going to use it. Okay. So Green's theorem and Green's formula, it's a pretty key theorem in multivariable calculus. But the way that we're going to be using it probably isn't the way that it was kind of intended, right? So these two formulas, even though they're the same. And so Green's theorem, Green's formula, they're kind of two parts of the same puzzle. The way that we're going to be using them is that we're going to be using them to basically give us a way to do integration by parts in multi-dimensions. Okay. Probably wasn't the original intention of these mathematicians is to help engineers, come up with something like FEA, but it's useful for that sense. Okay. So, just because of timing and I want to finish this up today, I'm not going to do the full derivation, but I am going to give you kind of the gist of it. Okay. Okay. So let's kind of review, what our integration by parts look like in 1D. And so integration by parts in 1D, specifically for our finite element problems, look like the following, right? So we have integration from x1 to x2 of our weighting function w of x times derivative d dx of quantity of k times a dt dx, all integrated over dx, okay? So that's our weak form integral that we obtained, after we multiplied our equation by our weighting function and after we applied our integral, okay? Right? And so what we did, because what we said from here is that, this equation right here has an unbalanced derivative, right? So we have this weighting function w, we primarily applied integration by parts to move the derivative onto w, okay? So what we said, this has an unbalanced derivative. And so by applying integration by parts, we obtain the following results. Okay? First, we have quantity w of x times k times a dt dx. Okay. Evaluated at x at the Neumann boundary. Okay. Minus integral from x1 to x2 dw dx times k times a dt dx dx. Okay. So we basically perform integration by parts, shift the derivative onto the W term, but then in doing so, we get kind of this extra term that comes out, okay? So what we have here is a term that's only evaluated on the boundary. So this is what we call a boundary term. Okay. And then we have this, term right here, which is an interior term, right? So it's still an integral, but it has a balanced derivative. Okay. And so if you want to think even further ahead, that boundary term there is eventually going to become part of the element forcing vector. And then this balanced integral term, this becomes our element stiffness matrix. Okay. All right. So that was kind of the main purpose of our integration by parts, right? Is to kind of balance the derivatives and to kind of pop out this boundary term. Okay. So when we're in multiple dimensions, right, in 2D, 3D, our goal is the same, right? So we want to kind of get the same things. It's just that how we get there is going to involve, these multivariable calculus, these vector calculus operators, as well as utilization of Green's theorem or Green's formula. Okay. So again, I have a full derivation of this in the notes. We're not going to go through it. I just want to get you the kind of the gist of it. Okay. So by applying Green's theorem and Green's formula, we're going to get the same notion here, where we're going to go from a form with an unbalanced derivative, okay, to a form with a balanced derivative and a boundary term. Okay. Okay. So I'm just going to show you the form in 2D. Although in notes, I do have the form for 3 dimensions as well. Okay. So let's start on the left, right? So our starting point for integration by parts is always an integral with an unbalanced derivative. Okay. And so in 2D, that's going to be a double integral. Okay. So it's going to be integral over the domain. So we call that the integral over A. Okay. And then on this, we're going to take W of X and Y. Okay. Multiplied by K times A. Okay. Multiplied by the Laplacian of the temperature. Okay. So once again, we have a term on the left here with an unbalanced derivative. Okay. On the one hand, we have our weighting function W of X and Y that has no derivatives. Meanwhile, our temperature has a Laplacian applied to it, which means it's an derivative of order 2. Okay. And so by applying our Green's theorem or Green's formula, we get the following. Okay. On the one hand, we get a line integral, okay, around the boundary of A, okay, of W times gradient of T dot product with the normal vector. Okay. So this right here is a line integral around the boundary. Right. Remember we talked about earlier today that the boundary of a 2-dimensional domain is a line, right? And so instead of just having a single kind of evaluated term, we have a line integral. Okay. You can see the normal vector is making an appearance there as well. Minus double integral of the gradient of W dot product with the gradient of t. dA. Okay. Or it's not dot product, excuse me, it's just regular multiplication. So this right here is our balanced our balanced integral with the balanced derivative. And just like we have above, you know, these two terms here are going to play the similar roles. Okay. So this line integral around the boundary, this is going to become our element forcing vector or part of our element forcing vector. And then this integral with the balanced derivative, this is going to become our element stiffness matrix. I forgot Ka. It is K here. K is not important. It's just most times just a constant. Okay. K here's. All right. Any questions on this before we wrap it up for today? Okay. All right. So we'll pause here for today. And so when we come back on Thursday, we'll see this put in action. And so we're going to start with heat conduction problems in 2D. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you guys on Thursday. Do you have a bunch of updates, Lalo? If you want, we can meet on Thursday. Just 'cause I know we just met last Thursday.
Actually, if you have time, I have been able to get some stuff working, and so if you wanted to talk about that, completely up to you.
Oh, sorry, the volume was down. Say again?
Oh, I said if you have time, I can definitely come in today because I got stuff running and working, and
Okay.
if you wanted to chat about it.
Yeah. Let's talk today. Let me go back to my office and then I'll hop on our
Okay, no worries. I just wanted to double check.
Okay. Yeah, sounds
All
good. All right. See you.